Our second problem is Lucy and her friend are working at an assembly plant making wooden toy giraffes. At the end of the line, the giraffes go horizontally off the edge of a conveyor belt and fall into a box below. If the box is 0.6 meters below the level of the conveyor belt and 0.4 meters away from it, what must be the horizontal velocity of giraffes as they leave the conveyor belt? This is an excellent example of your textbook really stretching to give you some kind of a plausible reason to do a type 1 projectile problem. This is kind of dumb, but we're going to do it anyway because it's good practice. So the thing that is going to be probably the trickiest here is just organizing the pieces of information they give you and what that is supposed to actually look like. So imagine conveyor belt. Here's your conveyor belt and giraffe toy thing. There you go, giraffe. And it falls, it says that it goes horizontally off the edge of the conveyor belt, and it falls into a box that is 0.6 meters below the conveyor belt. So we're looking for a vertical change of 0.6 meters, and the box is 0.4 meters, and that's my change in the x direction. And so my box is going to be right about, here. So it's falling 0.6 meters, and while it's falling, it's also moving outward 0.4 meters. So there is actually one thing that I'm missing in this diagram. Can you spot it? Or rather in the labels? It is, that should be negative. It is going down. Okay, let's go ahead and list our information in the x and y direction. So x, y, okay, change in x, horizontal velocity, change in time, change in y, acceleration, time, initial velocity, final velocity. My change in x, my change in horizontal position is 0.4 meters. My x, my horizontal velocity, is what I'm looking for. Change in time is not given. My change in y is given, that is negative 0.6 meters. Acceleration, negative 9.8, unless otherwise given to you, sorry. Time is not given. Initial velocity in the y direction, it's a type 1, it's 0 meters per second. So again, in this problem, I have more information on the y side, so that's the side that I need to start on. So we again need to calculate time because time is our link between the y and the x side. So I'm again going to use the equation delta d is equal to 1/2 at squared plus v initial t. Again, v initial t is 0 because my initial velocity is 0. My change in position is something that I can plug in. I need to solve for t here, so I'm going to do my square root 2 times change in position over acceleration is equal to t. So that is equal to the square root of 2 times negative 0.6 meters divided by negative 9.8 meters per second squared, which is 0.3499 seconds. Okay, now that I have that time, I'm going to figure out what my velocity was, my velocity on the x side. So I now need to use my equation 4, and we know d final is equal to velocity times time plus d initial. and we also know that this can be rearranged as velocity is change in position over change in time. My change in position is 4 meters. Positive, it's going forward. And my time is 0.3499 seconds. My velocity equals 1.14 meters. And the correct answer should actually only have 1 sig fig because both 0.6 and 0.4 only have 1 sig fig. So that's technically 1 meter. Per second. Okay, problem number 2. Time for problem number 3. You are visiting a friend from elementary school who now lives in a small town. Local amusement park is a local amusement is an ice cream parlor where Stan, the short order cook, slides his completed ice cream sundaes down the counter at a speed of 2 meters per second. Yeah, we know that. The counter is kept very well polished for this purpose. Basically, they're trying to say it doesn't decelerate due to friction, so it's going at a constant speed as it slides across, unlike our lovely marbles from our lab. The counter, if servers catch the sundaes 7 centimeters, it gives you centimeters, so you do have to convert that to meters. From the edge of the counter, how far do they fall from the edge of the counter to the point at which the servers catch them? Okay, so we've got the counter here, ice cream sundae thing, there you go. And it slides with a velocity Vx of 2. Okay, and it says that they catch them 7 centimeters from the edge of the counter. How far do they fall? So is that 7 centimeters, is that going to be change in x or change in y? It's the change in x. Good. So we don't know, as they're falling, we don't know what delta y is, but our delta x has to be 7 centimeters. So 7 centimeters, we know in every meter there's 100 centimeters. So I'm going to make that 0.07 meters. Okay. Now we're going to list our variables, x, y. All right, on the x side, delta x, velocity in the x direction, change in time. Delta y, acceleration, change in time, initial velocity, and final velocity. Delta x, 0.07 meters. Velocity in the x direction, 2.0 meters per second. Time, don't know. Change in y, that's our whole goal. Acceleration, negative 9.8. And time, still don't know. Initial velocity, 0. Final velocity, don't know, don't care. Okay. This time, we're only given 2 pieces of information on the y side. We cannot solve for these other variables. So we've got to go over to our x side. We're given 2 pieces of information, and there's only 1 more piece, so we can solve for that. So we're going to use equation 4. Delta x, delta d, is equal to vt. All right, so we know that we're solving for time here. So if time's over on this side, we're going to divide by velocity on both sides to get time alone. So delta d over v is equal to delta t. Plugging in that information, 0.07 divided by 2 gives me 0.035. Very small amount of time. Now I can plug that time over into the other side, and I'll be given acceleration, time, and initial velocity, and I want to solve for my change in y. So I need an equation that will solve for change in position in the vertical direction using one of my constant acceleration equations. I don't have final velocity, so I can't use 3. Number 1 doesn't have change in position in it at all, so I need 2. So 2 is change in position is equal to 1/2 times acceleration times time squared plus v initial t. Again, v initial t is going to be 0 because my initial velocity is 0. Change in position is going to be 1/2 times negative 9.8 meters per second squared times my time squared, which is 0.035 seconds squared. Delta D is equal to 0.00600025 meters. Yes, it is very, very small. Why? Well, the time is really small, so it's not going to go very far. Now, to give this the correct number of significant figures, I've got 2.0, which has 2 significant figures, and I have 7.0, which is 2 significant figures given to me in the problem. So my final answer is going to be 0.0060 meters, or write it 6.0 times 10 to the negative 3rd meters. And you're done. All right, thank you guys for watching. See you in class on Tuesday.